So we're going to be working on two sections of Newton. They're in one section in the book I used to use, so I just kept the notes together. So Newton calls them toolkit functions. Other people call them parent graphs. And then we're also going to talk about piecewise functions, which are often challenging for students. So the first thing I want to do is run through the graphs that you should just know by heart instantly and be able to reproduce quickly. So the square root function, if we just draw a quick graph of it, it looks like half of a sideways opening parabola, because that's what it is. And we have that the domain is positive x values only, and 0. So non-negative, basically. And then the range, you see that you get y values greater than or equal to 0. So you can write these as interval notation, but notice then you lose the information about which letter you're talking about. So if it helps you to write it as inequality notation, that's fine too. So that's the domain and range. Then the x and y intercept are the same. The only intercepts of this graph are 0, 0 for both. Then is the function even or odd? If a graph can be folded across the y-axis and match up, then it's even. So we don't have that. And if it can be reproduced by rotating it around the origin, it's odd, and we don't have that. So it's neither even nor odd. And then is the function increasing or decreasing? We can see that it's always increasing. And then does the function have an absolute minimum? And if it is, what is it? And it's y equals 0. So when you're asked about a minimum, it means the smallest y value. If you're asked where does it occur, it would be at x is 0. So then let's take a quick look at Desmos and see how we could graph this. So I do SQRT for square root, and you can see that it looks like the graph that we just did. It's a little flatter than how I drew it, but you should just be very familiar with its shape. Okay, so let's go back to the notes and go on to the next graph, which is the cube root graph. So now you can put negative numbers into a cube root. So it has two pieces to it. It's like the cubed function laid on its side. So the domain now is all real numbers, and the range is all real numbers, because you can put any number into the cube root function, and you can get any number out of it as an output. So then the only intercepts, again, for number 2 and 3 are the origin for both. And then is the function even or odd? And in this case, it's odd, because if you take the part in quadrant 1 and rotate it about the origin to quadrant 3, it matches up. And it's symmetric. And then we write WR2 with respect to. It's symmetric with respect to the origin. And is the function increasing or decreasing? Again, this one's always increasing. If you look from left to right, it's always going higher and higher and higher. Does it have any local maximum or minimum? No, because it can go all the way down as far as you like and all the way up as far as you like in the y direction. So it has no local max or min. Oh, that was number 6. Okay, so let's go to Desmos and see how the graph looks. So I'm going to turn off that graph, say y equals, and we're going to do x to the power of 1/3, because we know that's the same thing. And you can see that the graph looks like the y equals x cubed graph turned on its side. And we'll learn more about that later when we talk about inverse functions, and you'll see why it looks like that. Okay, then we have the absolute value function. So basically the absolute value function looks like a V with diagonal lines that each have a slope of 1. And again, the domain is all real numbers, because you can put any number you like in the absolute value function. But then notice that we only get non-negative values out as the range. So you can also say the range is y is greater than or equal to 0 if that way of saying it makes more sense to you. And then again for number 2 and 3, we get the x and y intercept is a single point of the origin. And this function is even because I could fold it in half about the y-axis and it would match up. So it's symmetric, we say, with respect to the y-axis. And then is the function increasing or decreasing? Well, it's both. So it's increasing for x greater than 0 and decreasing for x less than 0. So we always read our graphs from left to right when we're talking about increasing or decreasing. And then does the function have any local max or min? We can see that the point 0, 0 is the lowest point. So y equals 0 is a local min, we say. Okay, then the next one we're going to look at is the constant function. Well, this is something that looks like f of x equals 3. So that is just the horizontal line, right, of y equals 3. See how important it is, though, to label your axes so you can tell which one's the line and which one's the axis. So this is a constant function. It's a horizontal line with a slope of 0. Then we have the identity function, y equals x. So that's the diagonal line. And then y equals x squared is your friend, the parabola that goes through the origin. That's where the vertex is at the origin. And it's symmetric with respect to the y-axis also. Okay, then we have the cube function. So it goes flat for an instant right at the origin. And let me do that one on Desmos so you can see how it looks better. So that is y equals x cubed. But let's turn them both on and see how, oh my gosh, one looks like the other one rotated around. And that's because they are inverse functions of each other. So there's the cubic graph. And then the 1 over x graph, this one actually comes up a lot. And let's think about how it must look. X can't be 0. So in fact, there's a vertical asymptote at x equals 0. So the graph cannot touch the y-axis. Then in quadrant 1, those are positive x values. And as x gets larger, so we're going to say x goes to infinity, y goes to 0, right? Because if your denominator is getting huge, your fraction is getting tiny. And then as x gets tiny, as x goes to 0, y goes to infinity. So this graph has an arm in quadrant 1 that looks like an arc, and it has the point 1, 1 on it. And you could find other points on it. And then it is also symmetrical about the origin, and so we get the mirror image looking piece in quadrant 3 because you have the same sort of thing going on, whereas x goes to negative infinity, y is getting closer and closer to 0, and as x gets closer to 0, y is going to negative infinity now. Okay, so those are your toolkit functions that you should know those graphs just backwards, forwards, inside out, like you know your name, and not have to sit and think for a long time about them, because we're going to learn a lot of transformations of those graphs. And the more confident you are with the parent graph or the base graph, the better the transformation part will work for you. So now let's talk about piecewise defined functions. And I think I'm actually going to break the video here and come back and do piecewise so that it's in 2 shorter pieces.